Hi, welcome to this class 18B, where we will discuss diesel cycles and diesel engines. And right now it's in the middle of the night, so I have to speak softly so that I don't wake up my family. My apologies for that. Today there won't be a movie by Wout. Don't worry, he will come back. And well, when I think of diesel engines, I literally think of diesel engines that you will find in cars, diesel engines that power trains, diesel engines in ships, or diesel engines that you can use as a temporary or backup power supply, electrical power supply. And if you think of ships, well, these have big engines, and in fact, the biggest reciprocating engine in the world is this guy here, this Wärtsilä Sulzer RTA 96C. Um, It's a beast of an engine, and we will see more of it a few slides later. Well, as usual, we would like to start with a recap of the previous class, 18A. Back then, we talked about gas power cycles. Um, Obviously, these use gas as a working fluid through all stages of the cycle. You can have open and closed cycles. We introduced a sort of an idealized, simplified model cycle called the air standard cycle. We will see that come back also during this class. We talked about concepts like net work output and heat input, also about thermal efficiency. And we talked about specific cycles like the Stirling cycle. There was also a nice movie by Wout about the Otto cycle. And in this class, we will add the diesel cycle to that. We also introduce you to some jargon describing reciprocating engines. We talked about the bore, which is the diameter of the cylinder. We introduced the concepts of bottom dead center and top dead center. And if you were wondering what this term dead center means in this case, well, that means the point during a revolution where the piston rod is aligned with the line that connects the piston with the crankshaft. Um, and there's also the stroke, which is the distance between the TDC and BDC points. And you can also define terms, of course, for the volume. This is something that Wout did during his movie. So you can define the swept or displacement volume. That's the volume that's being refreshed during a stroke. There's also the clearance volume. That's the volume that remains when the piston is in the upper position, in the TDC position. It's the minimum volume. And there's also the maximum volume. That's, well, the clearance volume plus the swept volume. And here you see a picture of a cylinder head of a car engine that has a couple of valves. It has multiple valves, 2 valves for the inlet and 2 valves for the outlet. Now, it's of course always nice to use your jargon in a real life case. And let's take a look back at this biggest engine in the world. I'm really impressed by that thing. Here you see a couple of pictures. You see, for example, these pistons. They fit in a cylinder that has a bore of almost 1 meter. And then there are up to 14 cylinders in this engine. Here you see a picture of the crankshaft with people underneath. And these are more or less to the same scale. So this thing is huge. And well, here you see a couple of terms that should look familiar by now. So this is the bore of almost 1 meter. The stroke of the piston is 2.5 meters, and it displaces 1,800 liters of gas. That's 1,000 times more than a typical Volkswagen turbo diesel engine does. Engine speed, well, You don't want to bring that to a dance party because it can't keep up with the average beat. But nevertheless, all these numbers are impressive, and it delivers. Uh, Here it is, 108,000 brake horsepower in total, and it uses about 250 tons of fuel. And I forget. Oh, here it is, 250 tons of fuel per day. These numbers are mind-boggling. Now about this diesel cycle. So what is it? Where does its name come from? Well, it was invented by someone called Rudolf Diesel in 1893. So this is another one of these 19th century thermodynamics geniuses. And the diesel cycle, and the way we will discuss it today, is an idealization of the internal combustion engine cycle of the diesel engine. And the diesel engine is, or the diesel cycle is executed in a reciprocating piston cylinder device like the Otto engine. It's an open cycle oil fueled internal combustion engine. Oil fueled means, well, the diesel is actually diesel oil or diesel olie as we call it in Dutch. And although it's in real life an open cycle, it's modeled as a closed cycle. And the cycle itself is then built up from two isentropic processes. Here you see a PV diagram, so you don't recognize the isentropic processes immediately, but they correspond to these curved segments here. And then there's one isobaric segment, and there is one isochoric process. The big difference between a diesel engine and an Otto engine is that the diesel engine doesn't need an active ignition by some spark device. It works by auto ignition. So a gas mixture consisting of air and fuel, diesel, is inserted into the cylinder under high pressure and high temperature, and it will auto ignite because the temperature is high enough. Now, the diesel cycle was developed in an attempt to approach the efficiency of a Carnot machine even better than was possible with other devices. And in fact, it bears a resemblance to the Otto cycle. The main difference is the process between states 2 and 3, as you can see in this graph. So to the left we have an Otto cycle, to the right we have a diesel cycle. And well, you could you see that these things are similar except for this part here, the step from state 2 to state 3. So in a diesel engine, auto ignition occurs when you're going from 2 to 3. That happens when the fuel is injected at high temperature and high constant pressure. Whereas in the Otto engine, the gas is ignited by spark. This takes place at constant volume. So these are the two differences. Here you go straight up along an isochoric line, and here you stay on the same pressure on an isobar. And here are the same differences, but this time expressed in the form of a table. So during the compression phase in the Otto cycle, it's actually a mixture of air and fuel that's being compressed, whereas in the diesel engine, it's air that's being compressed. And a big difference is the ignition. For the Otto cycle, there's a spark, which instantaneously, while the volume doesn't change really, leads to combustion. So the combustion is can be described as an isochoric process, whereas in a diesel engine, the ignition takes place automatically as soon as you inject the air plus diesel mixture. And this is done by a compressor, and while it does so, it maintains a fixed pressure. That's the one way of thinking of it, and that leads to this isobaric combustion process. So let me guide you through the diesel cycle step by step. We start here at state 1. Let me bring out my pointer. There we go. We start from 1, and in the PV diagram we move to state 2, which corresponds to, well, obviously to compression, and it's isentropic compression. The piston moves up, and we model this as a isentropic process, so there's no heat exchange with the environment. You can consider the environment, well, you can consider the cylinder to be isolated. So, well, when you compress a gas, then that leads to an increase in temperature. And in a TS diagram, it's an isentropic process, so we go straight up, no change in entropy. Now, the second segment, that's from state 2 to 3, that's the combustion. That's where we inject the gas or the air diesel mixture, which then automatically ignites and leads to increase in temperature. But we model this as, well, we model it as a closed system, and this combustion is modeled as heat going into the system at fixed pressure. During this process, and also in the previous step, work is done. You can calculate work by this well-known formula. You integrate the pressure over volume, and the work, the input work here you need actually to put work in to compress the gas. That's given by this green area under the curve. But here, because of the combustion process, you get some work out. That's this green area. You can also look at the heat that's going in. We treat this as a reversible process, in which case you can calculate the heat as an integral, but this time of the quantity TdS, noting that T itself is of course a function of S, so we can perfectly perform the integral. And the heat that goes into the system when going from state 2 to state 3 during the combustion is given by this red area under the curve. Well, in the next step, we go from state 3 to 4. This is when the diesel pump stops injecting the gas fuel mixture. So it will expand, but the pressure will no longer be maintained. The pressure will go down, and during the expansion, also the temperature will go down. And then in the final step of the diesel cycle, from 4 back to state 1, the initial state, this is when the combustion products are actually rejected from the cylinder. But again, we model this as a closed cycle. So we keep our gas, but we somehow remove all the heat in a reversible way. And in this case, we can write the rejected heat again in the form of an integral. Also here in the previous step, work is being delivered by the engine, and that's of course the area under the curve here. So now we are in a position to compute the net work that we get out of the engine. That's of course what we are interested in. And below here there's a table. The table to the left describes for each sub-process of the cycle. What happens to the heat, whether heat is added or taken out, whether work is provided or work has to be provided to make it work, and the type of process, isentropic, isobaric, isentropic, and here you see isometric. That's of course just a synonym to isochoric, fixed volume. And then this table here to the right shows you again, well, in this case for each state, what the corresponding state variables are: temperature, pressure, volume, and entropy. Now the diesel cycle, we model it as a closed cycle, and not only that, we model it as an ideal air standard cycle. So what are the important formulas? Well, we treat it as an ideal gas, and using the ideal gas, we will cast the ideal gas law often in a form like this. So if I would bring T over to this side, I have a ratio, V over T, and you see those ratios back, but here we moved the T3 that normally belongs here as a denominator to V3. We moved that to that side, and likewise for the T2. I think you get my point. Then these parts of the cycle, these are the isentropic processes. And for isentropic processes, we have seen in class 9, and you can also read about it in the book of Schengel in section 7.9. There are these isentropic relations. There were 3 isentropic relations derived that are of this form. So there's always this exponent involved, this K, and K is the ratio of Cp to Cv. We will use these a number of times, and also in the previous class in Wout's movie they were used, as you may remember. Well, it's a closed system, so we can apply the first law of thermodynamics in the following form. There's only heat transfer involved and work that's delivered, or is either delivered or has to be delivered. And well, remember also that internal energy changes are associated with Cv times delta T, and enthalpy changes are associated with Cp times delta T. For example, the input heat can be expressed using the first law of thermodynamics. It can be expressed in terms of an internal energy change and work that's done. This delta U here that's U3 minus U2. The work that's done, that's actually the change in, well, it's actually P times delta V. And this doesn't really look like P times delta V, but you have to realize that P3 and P2 are actually the same. So if you realize that P3 and P2 are the same, then it actually says P delta V. And then we recognize this is indeed work that's done. Hey, but now we can group this U3 and this P3 V3 together into the enthalpy H3. So we can actually rewrite this in a simpler form. And for this enthalpy difference, we can use this expression here, which is valid for an ideal gas. There's another important parameter that plays a role in determining the efficiency of the engines. That's called the compression ratio, the ratio to the maximum volume during a stroke and the minimum volume. We came across that during Wout's presentation, and also there he showed that using these isentropic relations, these guys, you can show that the ratio of V1 to V2 is the same as the ratio of V4 to V2. In diesel engines, there's an additional parameter that doesn't play a role in the Otto cycle, and that's the so-called cutoff ratio. That's ratio from V3 to V2. And if we look here in the PV diagram, that actually corresponds to the ratio of the final volume after the combustion phase to the initial volume of the combustion phase. And that also plays a role in the efficiency of the diesel engine. We will see that later. And well, there is a maximum pressure involved. There's a minimum pressure involved. Same for the temperatures. And I think that's pretty obvious from the PV diagrams, for example, and the TS diagrams. Now let's take a look at the work output and heat input of the diesel cycle, because that's what you can, these are the ingredients to find the efficiency. Let's take a look at the heat input first. So again, we're treating this following the rules or the rule of thumb provided by the ideal air standard analysis. So during the combustion, heat goes into the cycle, and there's also work associated with this process. That's the change in volume at constant pressure. Remember that P3 equals P2 here. So what's written here is actually P delta V. Now, the first law for a closed system, remember we're modeling this as a closed system, says that the change in internal energy is the heat that's added or removed from the system and the work that's done. And well, we can write this out. We saw something similar on the previous slide. And it turns out that the work that is again written in this form here, this P3 and P2 V2, can be combined with the internal energies and expressed as enthalpies, and then we can write the change in enthalpy in terms of the Cp times delta T. Okay, so we figured out how much heat goes into the system. Now let's try to find out how much work comes out of it. So, well, the network is, of course, the sum of the work that has to be delivered or is delivered during each process. Work is involved in each of the 4 processes except for this one. Here there is no volume change, so no work is done. But during the combustion and also the isentropic expansion, the piston cylinder delivers work to the crankshaft, whereas during the compression, of course, work has to go into the engine. Now, these curved parts, these are isentropic processes for which we assume that the cylinder is perfectly isolated from its environment. So the expansion is reversible and isentropic, and there is no heat transfer during these 2 processes. There's only heat transfer during the combustion and the heat rejection. Now again, we can apply the first law of thermodynamics. We write down the various changes in internal energy and the work that's done using the first law. Again, you will notice that we hang on to the notation P3 and P2, although they are basically the same. And that makes it easier for us in this step to regroup the terms and express everything in terms of enthalpy again. No, not everything, but some of the terms can be grouped to enthalpies. Some will stay in the form of internal energies, and it turns out that the net power that comes out is a term that's Cp times T3 minus T2. That has to do with the combustion. And there is the term that has to do with the heat rejection here. And remember that we can write down these expressions only for an ideal gas, that the change in enthalpy is as simple as Cp times delta T. For example, for the internal energy in one of the previous classes, I think that was 17b, we saw that the internal energy, well, the full expression for changes in the internal energy, if it's not an ideal gas, is actually much more complicated with all these different terms and factors. So this ideal gas approximation really makes life simpler. So, okay, we found the net work output of the diesel cycle. That's expressed by this first equation. And I thought I had my pointer out, and now it's gone again. Here it is. We derived this on the previous slides, just like the heat that goes into the diesel cycle. So we're getting close to finding the efficiency, but these are expressions that give specific energies that are valid for only one stroke, because we were looking at this idealized model. And a diesel engine, like a four-stroke Otto engine, is a four-stroke engine. So we need to take a few more steps before we can compute the power output and things like the efficiency. So a four-stroke engine involves four strokes, and during these four strokes there are actually two revolutions of the crank or the crankshaft, but only during one stroke, so only during one revolution, power or work is actually delivered. Now a diesel engine, the number of revolutions per unit time is typically expressed in revs per minute, and power is expressed in joules per second, so we need to have an additional conversion there. So the specific power of a diesel engine is, well, here it is factor 1/2 that accounts for the fact that only one revolution delivers work and the other revolution is only to get the combustion products out and get the fresh air in. And here is the conversion of revs per minute to basically revs per second. So we get the specific power, but diesel engines, they typically have more than one cylinder. So we have to multiply this with the total mass that's going through these cylinders, and then you should not forget to multiply it also with the total number of cylinders, which could be 14 in the case of this gigantic Wärtsilä engine. So if we multiply the specific power with the mass flow, then we find the total power that can be delivered by a diesel engine. And this guy here can deliver 80,000 watts or something. Wait, did I say 80,000 watts? I think I meant 80,000 kilowatts. Okay, now let's move on to the efficiency of the diesel cycle. Finding the efficiency is now a bit more complicated than previously in the Otto cycle, because there is this additional cutoff ratio that plays a role here. And like we saw a few slides ago, this cutoff ratio is defined by the volume ratio. It's the V3 is the volume right after combustion, and V2 is the volume right before the combustion phase starts. And using these isentropic relations that we also encountered a few slides ago, when I was referring back to previous classes in the book of Schengel, using these isentropic relations, we can convert this volume or specific volume ratio to a temperature ratio. Okay. Well, as a matter of fact, we can write the ratio T4 to T1 in terms of pressures and in terms of this cutoff ratio, but this time to the power K. And remember that K is the ratio of Cp to Cv. Now with these equations, we can try to find the efficiency of the diesel cycle. So there's some math here, and it starts with the efficiency equation, which saying it in an intuitive way is the fraction of the thing you want to come out. That's the work that's delivered by the engine divided by what you have to put in, or what you have to use to pay for it. That's the total heat that goes in. So this is W net, but it's W net that comes out of the system. Well, I think these steps are not so difficult to explain by yourself. So maybe I shouldn't spend too much time on it right now. You can pause the video and see if you understand the steps, but it's basically the same as what we have done on the previous slides. And now it gets interesting, because we can, using these expressions and what we figured here before, what we figured out using these isentropic relations, now we can cast it in the following form. Maybe at first sight this doesn't tell you much, but let me tell you this. So this here is an expression for the efficiency of a diesel cycle that only depends on the ratio Cp/Cv of the gas mixture, and on this compression ratio Rv and the cutoff ratio, and that's it. These are the ingredients that you need to estimate the efficiency of a diesel engine. Well, okay, we understand that, but what does that mean, and how does it relate to the efficiency of an Otto cycle? Well, what you see here are a number of efficiency curves as a function of the compression ratio of the diesel engine. So these are curves for a diesel engine, using again this expression here that we derived on the previous slide. And you see that if the cutoff ratio RC, if the cutoff, yeah, this is a bit confusing, but here's called RC, and here I'm calling it R cutoff, but these are the same things. When this cutoff ratio decreases from 4 to 1, our curve actually starts to approach this one here, which turns out to be equal to the efficiency curve of the Otto cycle. Actually, I wanted to show also the expression for the Otto cycle here. The Otto cycle efficiency is basically this term here, this the stuff between parentheses to the power k minus 1. This stuff is this fraction is not part of the Otto efficiency, and also this 1 over k is not part of it. And then so you have 1 minus 1 over Rv to the power k minus 1. So how does that work? This is confusing. At least it was confusing to me at first. But it turns out that if you let R approach 1, that's what we were saying here, then the limit of R approaching 1 of this fraction becomes K. So the K cancels against this 1 over K, and what you end up with is indeed the Otto cycle efficiency. Then I would also like to introduce you to another concept, which is called the mean effective pressure. It's a convenient measure that you can use to judge whether it's beneficial to have an Otto or a diesel cycle. What do we mean by this mean effective pressure? Well, here is a PV diagram showing the diesel cycle. You can tell it's already a bit more like a real life cycle. It has rounded off corners. It's not actually, what is it? This part looks like an Otto cycle, and here it looks a bit flat like a diesel cycle. So it's already sort of a hybrid form, something from the real world apparently. But there is a maximum volume and there is a minimum volume. So there is a compression ratio. And there is a work that's done or that comes out of the engine. That's the enclosed area here. And we can write, or we can choose the mean effective pressure such that the area enclosed here between V minus and V max and between 0 and the mean effective pressure, that this area here equals the area inside the cycle. So mathematically, you would cast it in this form. Now, of course, the difference between Vmax and V minus, and after this class, or maybe right now, you may want to look up what Vmax minus V minus, or Vmax minus V min, what it is actually called, whether that's the swept volume or clearance volume. I'm pretty sure it's one of them, and you can figure out which one. Now, this is of course proportional to the size of the engine. So now engines with a larger pressure, so this PME is basically this MEP here, this is the same thing. So larger engines and engines with a larger PME produce more work per unit volume. And for that reason, engines with a larger mean effective pressure tend to be more practical. So it's something you want to remember. And if you come across a data sheet or what have you for some sort of reciprocating engine, then you will recognize, hey, this mean effective pressure, that's an interesting quantity. Now here's my favorite subject, the turbo. I don't know which of you boys and girls has a car, and if you have a car, whether that's a turbo diesel or perhaps an old-fashioned Saab with a turbo. But I've always loved turbos in my cars because they give you so much additional power, and in particular, it gives you torque. So how does this turbocharger work? Well, it's thermodynamically speaking, it's a device that you can use to enhance the output power of a diesel engine. By the way, you can also use it for gas engines, but in this example, we will look at the diesel engine. And a turbocharger consists on, well, it's basically one shaft with first a compressor, and at the end there's a turbine that is used to drive the compressor. It's something we have seen in block 4 several times as well, this combination of compressor and turbine. And you may want to look up what I'm talking about. And here is a picture of a typical turbo. So now how does that work? This compressor, this we put before the cylinder inlet, and what it does, well, it's being driven by the turbine, and it compresses the air. So the air comes in at a higher pressure when it enters the cylinder. So there's more mass going into the cylinder. There's a higher density, and the mass of air, and in particular the oxygen, is higher, and you can let in more diesel to have that combusted. So while you keep the air-fuel ratio fixed for optimum combustion, you burn at the same time more fuel, and you get a higher power output from your engine, higher torque, for example. And how does this turbine work? Where does it get the hot gas from that actually propel it? Well, these are actually the hot gases that come out of the exhaust of the cylinder. So it's the hot gases from coming out of the engine that drive the turbine, and then the turbine drives the compressor, which gives you the extra boost. And I still enjoy my turbo diesel every time when I drive it. Well, you may suspect that there is more to life than just ideal Otto cycles and ideal diesel cycles. And one cycle that you may encounter is the dual cycle, which is sort of a hybrid between an Otto and a diesel cycle, and which can describe real life cycles more realistically. And you may look into the book of Jengel in section 9.6 to read more about the dual cycle. And here is a PV diagram that shows the dual cycle. And what you will notice is that there is this additional point X that's being drawn here. And this makes a lot of difference. Because if I place, for example, my volume 3, if I would place that at the value of volume X, this basically means that I have to go up this isentropic curve until I reach this spot here, and then I go to point 2. Or as a matter of fact, from point 2 I would go to from state 2 I would go to state 3 up here, and that looks like an Otto cycle. On the other hand, if I would keep on going on this isentropic compression curve, and if I wouldn't stop at state 2 here, but if I would keep on going until I hit the pressure of point X and then go to 3, then I recover my diesel cycle. So this point X, the location of point X in the PV diagram, is sort of a parameter that allows you to play with the, well, let's call it the amount of Otto character and the abundance of, or the amount of diesel character. Well, as you can imagine, analyzing such a cycle is, again, a step more complicated than analyzing the diesel cycle. In the efficiency of the dual cycle, the parameters of interest are the so-called, well, the volume compression ratio between V1 and V2. So the ratio between the initial volume before isentropic compression and after isentropic compression. And also the volume expansion ratio when going from 3 to 4, again along the isentropic process. And you will see R1 and R2, these two, well, the compression ratio and the expansion ratio, you see these come back in this expression for the efficiency of the dual cycle. And you also see this pressure at point X. So these determine the efficiency of the dual cycle. And again, this dual cycle is a model that more closely describes real life cycles, in particular those in modern high-speed compression ignition engines. Okay. Oh, and I would like to point out that this is not within the scope of the exam, but nevertheless good for you to at least have seen it once. Now, before we conclude this class, I would like to guide you through an example calculation. And it's getting later and later, and I hope my brains will be able to keep up with what I'm trying to say. Okay, so we want to look at a Otto cycle given within the ideal standard air approximation. We're talking about a cycle with a compression ratio of 8. The inlet conditions are, gas fuel mixture at 300 Kelvin at a pressure of about atmospheric pressure, whereas the maximum pressure inside the or during a cycle is 3 megapascal. Now the question is, we would like to know the net power output of this engine and the heat that is transferred to the engine per kilogram of air, and we also would like to know the thermal efficiency. And for this, we can assume a fraction Cp to Cv of 1.4. So Cp to Cv, that's also denoted as K. And you may wonder, what Cv should I be using now? Well, it's the ideal air standard Otto cycle. So it's Cv of air. And in this case, it's at 300 Kelvin. Now let's take a look at the solution. So P3 in this diagram here, that's obviously the maximum pressure, and that's this 3 megapascal. So here we have one piece of the puzzle. A compression ratio of 8 means that this RV is equal to V1 over V2. And from the isentropic relations, remember, we could derive that V1 over V2 is equal to V4 over V3. So this factor of 8 applies to these two to the ratios as shown here. There's another piece of the puzzle. The heat transfer to the engine, well, we can't find that just in the snap of the finger, but we can start by writing down the expression for the heat. Assuming an ideal gas, because it's the ideal air standard Otto cycle, so we can use the relatively simple expression for the heat that's transferred to the engine. And of course, you may wonder, wait, what's going on? Well, it's the first law of thermodynamics. There's a change of internal energy. There's a corresponding heat that's being added or removed, and there's work that's done. And the sum of these, that's the internal energy change. And we're talking about this process here from 2 to 3. Hey, and there's no volume change, so there's no work done. So all the internal energy change, which for an ideal gas is given by this expression, must be equal to the heat that goes in. Okay, so we figured that out. Well, on the previous slides, we have seen how we can derive the net output power, or the work delivered by the engine. And we could express that as these two terms here. You may want to scroll back to find out how that went. And now that we have Qn and W net, we can find the thermal efficiency, because remember, it's what you want to get out, and how much you have to pay for it, the heat that goes in. Okay. We want to actually find the numerical value. We need to know the temperatures in all the 4 states of the cycle. So we have to find all the temperatures, and at this point we only have one, this 300 Kelvin. So how do we proceed? So in blue in this table are the values that were already given, or things that we have derived in the meantime with some clever thinking. But how to fill out the rest of the table, and I'm showing the results here already, and we will see step by step how we obtain these. So first of all, when we look at this process from going from 1 to 2, that's this part here. This is an isentropic process, and we can again look at these isentropic relations. And as a matter of fact, this one here is one form of the third isentropic relation. And since we know K, we can compute P2. And why can we compute P2? Well, we know the initial pressure, and we know P1, and we know the compression ratio, and we know K. So that's how we figure out P2. Good. We have P2. We already had P3, so we're almost there as far as it concerns the P's, the pressures. What about the temperature? Here we use the simply the ideal gas law, and you will notice that we also use this compression ratio here. Now this tells us T2, the temperature. So now we have and the pressure and the temperature of state 2. Now the next phase, or the next state that we consider is state 3. And here you may notice that my brains are starting to slow down, so I have to perhaps add a bit more fuel to them. Here we apply again the ideal gas law to find T3 from the ratio between P2 that we know, P3, we know that one, we know V2, and V3 is, oh, that's easy because we're talking about an isochoric process. Great. So we know what the temperature in state 3 is. Now going from 3 to 4, that's an isentropic expansion. So we can use one of our isentropic relations again to find the final pressure of this process, which turns out to be this 0.16 megapascal. So notice there's still some overpressure at the end of the cycle, just before we get rid of the combustion gases. And now the last step is to again use the ideal gas law, and using the known compression ratio, just like we did in this step, we also use the known compression ratio, and here we use the compression ratio of 8 again in combination with the gas law, ideal gas law, to find the final temperature at the end of the cycle. That's 489 Kelvin. And now we know all the temperatures here, and we can plug that into the previous equations that we had. We can find the heat that goes into the engine during one cycle. We can find the work that's delivered by the engine, and we can find the efficiency, which in this case turns out to be 56%. So I hope this was more or less clear, this explanation. Now, this was the final class, at least in the form as you've seen them over the past weeks. So what's next? Well, we still have a workshop on pneumatics and hydraulics in the planning, and this is something that that Wout will inform you about how this will take place. So keep an eye on the Canvas announcement, and of course, later this month there will be the exam. for engineering thermodynamics. All right, almost it. This is the slide with important formulas. And note here, there are these isentropic relations or isentropic processes for an ideal gas that we have used many times in the past class. So this slide is getting more and more useful also for myself. Again, thank you to Geni. And yeah, maybe a few questions you can ask yourself. So what distinguishes the diesel cycle from the Otto cycle? And a bit outside the scope of the class and the exam, but nevertheless very instructive is, well, you may want to read up or dig into the internet to find out why sometimes diesel engines are preferred over gasoline engines. Why do all these big ships have diesel engines, and the same for trucks? There must be a reason for it, and there are actually interesting reasons. And what I've noticed is while you read about this, you come across many of the concepts that you've learned about today, but you will see them in a real life setting. And so you may want to spend not too long, maybe when you're taking a break, 15 minutes or so. Okay, that was that. I hope to see you in the online meeting on Tuesday. Bye.